Okay, no other questions? Yeah.
So on one of the questions that I posted about using a cache, I know you didn't go over this in class. So can you explain if we need any initial initialization before you just use it? 'Cause I tried looking at the methods for the CSV base class, and I didn't find cache to be one of them.
No, no, you have to provide one.
I know, so how do you provide one? Because I think you just gave me the code how to use it, but
I see. So it would be a static field for uh, for that class, right?
okay.
And so the challenge I had when I looked at my solution is that it had that I had the cryptic comment that I had not never told you how to make a static field in Ruby, which I guess is true. So you could either look up how to make a static field, or you could call a static method that gives you that object.
So,
That's
so
the
you didn't
workaround.
just define it like inside a class called itself.cache or something? Could you have done that?
I the trouble is that you need a static object. You need well, maybe you don't. Um, no, I think you do, because when you look up something, when you have a relationship from say a question to choice, you need to be able to find choice objects, and so all of the objects need to be in a single cache, I guess. Or otherwise, I guess you could look at the choice class and have. That's another way of doing it that I hadn't thought about.
Because I couldn't figure that method out, and I went
All
ahead
right,
and
so I just instead of speculating what 15 ways there of doing it,
yeah.
the way that I did it is I have a single global hash table, and you can put it really any way you want. And so you have that single global hash table. The keys for that hash table, I concatenate the name of the class and the ID. I figure that's a unique key for the object.
Right.
And then the only question is, how do I get at that object? And if you look up how to make a static object in Ruby, you can just use that.
So you create a constant variable via hash table where you use that as a cache,
The
basically.
hash table is the cache.
Okay. Because I went the other way. I went ahead and just created constants and removed them so I basically use the constants as my cache.
Yeah, that's the same thing.
Okay.
That's the same thing.
I just wanted to.
Yeah. So you can any way that you find for defining a global object. I suppose it would even work if you just declared it outside all the other classes in your RB file. If you simply say cache equals empty map,
Oh, okay.
it would be accessible. Right? That would be the total brute force way of doing it.
Yeah, there's so many different ways, but
That's Ruby for you.
I went with the constant.
Any way that you got is fine. I don't care about the details.
So the extra day is just for part three,
What's that?
the extra day is only for part three?
Well, since people complained that they did not know about that twist and they might have worked at them in different orders, you have the extra day for everything you want.
For everything. Okay.
Yes.
For question number 2, you mentioned there could be multiple belongs to.
Yes.
Can you give us an example?
Yeah. Like if you have a course, and does a course belong to an instructor? Yeah, I guess why not, right? And a course could also belong to a department.
Okay. Can number 2 implement many-to-many relationships?
No. No.
How do you import the CSV files in number 3? Do you
Oh,
just
you don't import them. You don't import them. It's up to you how you set up the database, but when you look at what I did, I just typed these commands into the console. I would do it the same way. And now, someone pointed out that I did it wrong, that the way I set up the database in number 3, that the correct answer is always the first one. And that person is right.
Yes, exactly.
So there's some better way of doing it. So look in Piazza on the non-dumb way of doing it. So the way I had it is that, as you see if you do it my way, that the correct answer is always A.
The first choice would be the
Yes.
correct answer.
So, it would be elegant if you could avoid that. Yeah.
I don't know if you answered this one, that I asked last night. It was that you posted a test that said Q answer should be equal to Q choice number
Oh,
two.
there was a question whether it was 1 or 2. It's entirely possible that I messed up and looked at the wrong row or
Okay.
column somewhere.
Because you're not assuming that it always has to be in the same, position, 'cause it could be either one of those.
Oh, I see what you said.
On the question, Q answer is equal to.
Yes. No, I'm not assuming that they're always in the same position.
Okay.
And I think this actually might have been a consequence of my other stupid error, where I had them in the wrong position.
Okay.
So maybe the two of them have the same approximate cause, and that I set up my data the wrong way.
Okay.
I will, when I run the test, I will double check that. Now, someone else said, when I mean equal, does it mean they have the same hash code? And yeah, that's basically what I would be looking for.
Yes.
You know, if there's some issue with the order and I don't have the energy to actually account for that, I might just look at the hash codes. But that's exactly what I mean. Other questions? Yeah.
Question 3, once you picked out your choices for the questions and you probably press the button to say submit the quiz.
Yeah.
I guess I was wondering how that could be implemented.
All right. So you should have a form. Let's see if I can draw in here. So I put all of the questions on one sheet instead of. I guess you could ask one question per page, but I wasn't smart enough for that. I just put all of the questions on a single form, and on that form, and then I loop through the choices as well. And let's say I want to be as lazy as possible, then I just put text fields here instead of fussing with radio buttons. Right? And then I need to give each of them a different ID. And I suppose you could just, as IDs, you could just use the number of the question. Right? And then the user fills in some stuff here. And then when you come into whatever the thing is that receives the answer, then that thing gets a param that'll map 1 to A, 2 to B, I guess A is not really a good choice, right? So I'd say that's to A. And then it'll have some other garbage in there like submit equals submit or whatever it is. And then you need to loop through the things in the param, fish out what the answer is, see if it was the correct answer. If so, you increment a score counter. And then in the end you say, congratulations, your score was 0.
And this is done in the controller.
Yes. And whatever the gizmo is that processes the answer.
On the same, and the result will display on the same page?
No, it just shows a new page. I think it's more work to show it on the same page. So I just show a new page, and the new page says the score.
And will this new page need its own view?
What's that?
Will this new page need its own view page?
I guess, yeah.
Yeah, it has a personal page too.
But if you find it simpler to put it on the same page, go for it. I don't care. I haven't really thought this through. That it might be simpler now that I think about it. It's just, at first you're going to say your score is 0, and then they're going to click on this. I don't care. Whatever, I really do not care whether it's functional or pretty or anything. I just want you to put the basic functionality in so that you get some idea where the different pieces are. So you can choose the lamest solution that can be construed to be workable. I really don't care how you do it. But the way I did it is that I put all the questions on one page and then I did an answer page. And no, I don't remember how I did it. Yeah.
So you don't want us to modify anything on the questions and choices, right? You don't want us to.
Yeah, so someone did that and said, oh, I stored the answers in the database. And at first I said whatever, but then once I started thinking about it, I realized that that's actually really bad, because if you have more than one user, which I think the aspiration of every web application is to have more than one user, then you can't store that stuff in the database unless you have a separate table for users and responses.
Right, but I mean like the table that has the questions and the choices, you don't want us to have any mechanism to add.
Oh, no.
Choices. You just put them in and then we just use them.
That's right. That's right. Someone could use the CRUD screens to add or write a web service. I don't care about that. I want you to write, really, just
take the quiz.
Just take the quiz. Take this particular quiz. I don't want you to write a whole web application. I want you to write an itty bitty piece of the web application. And my motivation is I just want you to see a few aspects of what Rails does. And you will shortly see why I want to do this, because you're going to compare it with Scheme. Turns out you can write web applications in Scheme, and it is only 10 times easier in Scheme. It's hard to believe, but it really is. So, and you will not believe that until after you have suffered through the Rails one. All right, continuations. So a continuation is a control structure that probably none of you have ever seen before. So it lets you do things. It lets you simulate other control structures, and that's really the why we care about it. Now, what it does is it captures a point of the computation that you're doing. So imagine your program is trundling along, and now at one point you take a snapshot. And now why might you want to do that? You want to do it because you want to come back to that later. And that turns out to be a very powerful feature, as you could imagine. Wouldn't you like to be able to do that in life? You know, there are moments to which you would have liked to return, either to relive them in the same way, or if your life is like mine, to change things and live them differently, right? So, and that is really what a continuation is. It's a way of saying, mark this point in the life of the program so that one can later come back to it in exactly the same way. Kind of like time travel. So, why would you want it? Like one example for its usage is you can implement exception handling with continuations. With exceptions, you have this nonlinear control flow, the throw, and so you can, if you put a continuation, a snapshot at every try block, and then when the throw comes, you can go back to one of the try blocks. Exception handling is a little limited. When you find the exception and you throw, you get back out to an outer point of the program. What if you wanted to retry? Let's say that there was a file not found exception. Then the throw goes to some outer level where one asks the user, give me another file name. And then the way you have to code it up right now is you have to code up a loop. But with continuations, you can go back to the point of failure with a new file name in hand and say, let's just retry it there. You can implement a resumption facility. No programming language today has that because it would be difficult to do it in general terms. But if you want to do it in specific situations, you can do it in a language that has continuation. You can do, so as an example of where you often want to come back, imagine that you do a search on a tree. And you know how it goes. You go here, you go there, you go to various places. And how do you deliver the search results? You could collect them all and give the whole thing back, or you could call a function. But really what you kind of want to do is you have found something interesting. Then you want to give it to someone to process it. Then you want to resume the search. With continuations, you can do that. So anytime that you want to interrupt and you want to resume something, continuations are your thing. Now, we're going to study them in Scheme because, as you'll see later when we look at them in Scala, in Scheme they're fairly easy to understand. It's a complicated subject, but they're easier to understand in Scheme than in most other languages. In Scala, there's a type system that really gets in your way, and in Scheme we just don't have that. So, Scheme has a primitive operation called call with current continuation that was there to give you access to these snapshots. So call, and it's always abbreviated as call CC because the other thing is too long. So call CC is a function that takes one argument. And so when you call CC, you pass it a function. And the result of that is the result of calling f. Now remember, f is a function, it has an argument, and that one argument is the current continuation. It's the spot in the program where the call CC is located. So the call CC is somewhere here. We're going to pass it a function that's typically a lambda. The function does a bunch of work. And this k here, thank you. Now, if I could just go back in time if I had a continuation. So here's my call CC. And so you can think of this as a place in the computation. And this place is given to the function that I had in here, the lambda k. So it gets injected in here, and you can later use it. So this k is also a function. It's also a function with one argument. And if at some point later you call k of some argument here, then it is as if this thing here had been replaced by a, and your program is run with that configuration. Now, if you understood any of this, yes, no one does at this point. Neither did I when I first saw it. So we're just going to have to look at some examples. So over here, look at this expression. I have plus 3, and then I have this call CC in here. So you see this phenomenon that the call CC is inside some bigger context. So over here, my function f is lambda k 4. So the first rule said what happens with call CC is it gets a function and it executes that function. So now it's going to execute that function. That function returns 4. Right? It gets something, it returns 4. And the whole expression then takes this value here, puts it in the surrounding context, and you get the answer set. So this is a boring case because we didn't make any use of the continuation. We didn't make any use of the snapshot. So let's try to make some use of it. So over here, we're making the thing just as before, except now I'm making an effort to use my k. So we have to understand what the current continuation is. So let's see what it is. The current continuation is you take your entire program, except where you find the call CC, you kind of put a hole. You rip it out, and you put in a hole, and that's your parameter. So the continuation is really lambda hole plus 3. Continuation is the function that adds 3 to an argument. That's because the continuation was located in this particular context. I realize it sounds totally useless, but bear with me. So my continuation function k is this. So let's see what happens. So now I'm computing plus 3. Now I'm calling this thing here. This is f. With k is this thing. We're trundling along. We're applying k to 4. So what is k of 4? 7, right? Now it's actually a little bit more than 7. It is 7 and back to the REPL. because if you look at the context evaluates this thing, and then it displays the answer. And so that actually is what happens at this point. When you call k of 4, it shows the answer 7, and it's done. So the 39 here is we never get to this point. That turns out to be a little bit inconvenient, that the continuations kind of get you back to the read eval print loop, and we'll struggle with that a little bit in Scheme. There are variations of continuations called delimited continuations that don't go up all the way back to the REPL, but to another spot, and we'll see those later in Scala. But right now, that's what we'll do.
Can you please go ahead again?
Okay, I purposefully won't, because it won't do us any good. I'll go to another example, and then I'll come back to it. So the only thing that you can glean from this example, because it's so contrived and useless, the only thing that you can glean from it is that call CC takes a function. That function takes a parameter which is this weird continuation. When you call the continuation, which is again a function, then you get this filling in the hole effect. And we'll look at the details later. So let's do something slightly more useful and capture a continuation in a variable. So over here I'm defining kk to be just a blank thing as a placeholder. Now in my continuation here, so I get called with the continuation here, and I'm capturing it. Set exclamation mark is a mutation that we don't normally use, but here we have to. So we're mutating kk to now contain this function. So at this point here, kk is a function. And what function is it? Well, when we call it at our leisure with any parameter, then it returns 3 plus whatever. Because the function that kk is it is the continuation that you get by punching out all of this stuff. It's the plus 3 whole. And I can use it as often as I like because I've captured it. So a better way of thinking what kk is a jump to this point. And generally, what you want to do when you have a continuation is you want to capture it. A continuation that you don't capture tends to be pretty useless. So it's very common that when you make the continuation, the very first thing you do is you capture it for later reuse. Or let's look at the other way around. Suppose that you're trundling along in your program, and at some later point you say, gosh, I might want to come back to this point. Then what you do is you put your continuation here. You stash it away. And then you put your normal stuff. Whatever it is that you normally do, and then you go on your scheme on the merry way with your parentheses. So this is the mechanical way of taking a snapshot. Then at any time later you want to go back to this point, then you call kk, and then that gets you back in here. So that's the basic idea. Oftentimes one captures more than one continuation because sometimes you want to go back and forth between 2 points. And then you save 2 continuations and you invoke one or the other. And that's the thing I said before, what's kind of nasty with the continuation is that they capture the entire context right back to returning to the REPL. But if you make it so that on the return trip, it calls another continuation, then you can go back multiple times.
So is it like you have in your execution environment, you have like a stack of frames and you want to go back to the frame which is somewhere in the between,
Yes.
and from there start executing?
Yes, so essentially that is right. So what she's saying is is a continuation kind of like a snapshot of the entire stack and like all the registers. And that is essentially the right idea, because you could imagine that if you were to, at any point, restore all of that stuff, then you would come back to where you were. If you restore the program counter and all of the registers, you kind of go back. But it's actually a little bit more than that. and the way that it works in Scheme is the stack is destructive. It'll overwrite previous history. In Scheme, the runtime control structure is not destructive. It keeps a record of all the old history. So it's kind of as if the stack was a bunch of records on the heap, which is really what it is. So when you go back, then you go back to that particular configuration. And so, like with the let me try to say this another way. So with the stack, what happens is you have an activation record, and then you have another, and then you have another, and eventually this one goes away, and then this one gets overwritten again. But in Scheme, that's not what it looks like. It doesn't. They never go away. Instead, this one still stays around, and you might then get another one that points here. And what a continuation really is, it is then a pointer to this activation record. Because you have a pointer to it, it doesn't get garbage collected.
So this is how Scheme environment is all together. They build the stacks this way.
Yes, oh, absolutely. Yes, so it's not a runtime stack, but it's this runtime tree. Now, if you don't take a continuation, like if no continuation captures this frame, the frame will eventually get garbage collected. So it doesn't really keep all of the history. It keeps all of the history that someone wanted to remember. Yeah, so you might find that helpful to understand how these things work. So let's give a somewhat contrived idea on how to use continuations. So here I'm having a method that computes the product of a list of elements. So it's a recursive function that says if the list is empty, then the product is 1. Otherwise, the product, I take the head of the list and multiply it with the product of the rest. Kind of normal recursive computation. And now that's fine, but now look at the following code here, where I'm taking the product of this list here. Now, every multiplication that I do after this here is a waste, because at this point it's become clear that it's 0. Now, I could, of course, simply say that if it's 0, then return 0, but I would still have the work of unwinding this many iterations of stack. Yeah, it takes a little bit of work to return from the previous function. And so what I would like to be able to do is, at this point, simply get out completely as without unwinding the stack. And the continuation will let me do that. Now, it's not a truly wonderful example, because the cost of this, as we'll see later when we talk about tail recursion, yeah, it's not really worth using the continuation for it, but it shows the syntax pretty nicely. By the way, in Java, you could achieve a similar effect just with a throw. You could throw an exception, and that would unwind the stack in a kind of brutal way. So we're simulating that kind of thing with continuations now. So what our plan of attack is that when we see the 0 here, we want to escape. Where do we want to escape to? Somewhere to the very outer scope here. So, and the strategy is always the same. You want to set up the point of escape, and then you want to invoke it when the time to escape has come. So over here, I'm setting the point of escape. I want to get out at the top level of the lambdas. And then over here, when I'm ready to escape, then I call it. Otherwise, the code hasn't really been changed. Well, that's not quite true. The code has been replaced by some loopy stuff, and I'll show you in a minute why that is necessary. So the way to think about this here is this whole escape mechanism is, imagine you're a bank robber. And so the normal way of robbing a bank is tedious and dangerous. That you enter the bank, you get out with a loot just a getaway card, and just danger all this time. What is much better is that when you're in the comfort of your home, you take a continuation, you put it in your pocket, you do your bank robbing business, and when you're done, you invoke the continuation. And where will you be? Back home, right? That avoids all of that hassle with the escape card, the risk of getting snagged in traffic and all that. So it's an eminently useful concept here. So let's see, we can even carry a value back home. The value of the computation here is 0. And when we're calling it, it is as if a 0 had magically appeared at the place where we want it. The entire thing here, the entire call CC, has now been replaced with a 0, and the 0 gets returned as the function value. And it really is what you want. You want that bag of money to appear on your kitchen table. And it'll work just like that. So you just have to take the continuation. So you take the continuation when you're there standing on your kitchen table. And then you do your normal thing. You can do all sorts of things. You can brush your teeth, and you can show up at the bank. It doesn't really matter because later on you're going to invoke the continuation and you're back where you want it to be. So that's the intuition. Now, why did we have to do this thing with this loop stuff? So the first time that people do this, they typically try to set it up the following way, where here we're writing our function. We want to return to the beginning of the function, so we take up some continuation here, and we're saying, okay, if the head of the list is 0, then our whole product is going to be 0. So we want to get back and return the answer 0. But what's wrong with this thing here is at this point you're not getting back to the right spot. You're getting back to the previous recursive invocation. And that's no good because you're not saving yourself unrolling all of the recursive invocations. So that's why over here I have to do this code a little bit more complicated. And so now we do have to understand this letrec stuff here. So I wanted to make sure that the prod function itself was not recursive, because I'm returning to the beginning of prod, and I don't want this to be the location of recursion. So then I put my helper function inside here. The helper function is exactly the same that you've seen before. And I just had to rename it prod helper. And so I define it here with the letrec because that's how you make a local function definition. And then this is the entire definition here, and here is the call. I could have perfectly well defined letrec outside. Not letrec, prod helper. I could have defined it outside. It's just considered inelegant in Steam to have two global function definitions that depend on each other. So that's why I was making it as a local function. The syntax for a local function could be better.
Instead of using define, you use letrec because you want to use it right there.
Well, I can't do it, as far as I know, I can't do a define inside a define. A define is somehow special. It works on the global scope. I'll actually have to check that because I can't remember. At one point, a scheme dialect that I used had that restriction. And so I've gotten into the habit of only using define on the top level. I'll double check that. So it's not the greatest use case, but it does show the mechanics of it. And we'll see plenty of more exciting use cases. Now, for the jumping back use case. So the typical example where you want to jump back into something is tree iteration. So here I have a tree, and I'm writing this tree here just for simplicity as a list of lists. So if I write this tree down in tree form, I have a root. It has children 1, 2, 31, 41, 42, 33. Yeah. And then 5. Oh, no, that's right.
No.
No. Thank you.
2 has that. Should be.
I think the mistake I'm making is that the values, the numbers are only at the fringes of the tree. So the 1 and 2 were correct. And then this one here is a node.
Fine.
That's fine.
Yes.
No. It's this node here. Watch this.
Oh, okay. Kind of the whole parentheses.
And then we have a 5, and then we have a node. Yes, so every list is a subtree. So this is a notation for trees that have numbers only at the fringes, not like the trees you see in your data structures course.
Right.
And let's say for whatever reason we have such a tree. And now we wanted to iterate over it. In your data structures course, you've learned how to do how to use the visitor pattern, where you can visit them. So you write a function that recursively goes through the tree, and whenever it finds something that's worth visiting, which in our case is a leaf, then it'll invoke the function on that. So here's the code for that. I get a function and my list, which really is a tree. And if it's a list, then it's a subtree. I keep on going. If it's not a list, then I invoke the function on the element. And by doing this, I will recursively visit all of these leaves, and on each of them I call f. f of 1, f of 2, f of 31, f of 41, and so on.
F is a function which is defined somewhere.
Yes, it's whatever it is that I want to do on those nodes. I might want to print the contents. I want to make it added up to some global total. It's a generic way of traversing a tree. And this is, whenever you have a tree structure, you've had that problem in your data structures course. How can you make a generic way of doing something with that tree? This is what's called the visitor pattern. That says you have, if you do it in Java, you would have an object that does the visitation. In a functional language, you have a function that does the visitation. Now the trouble with this visiting scheme is that, let's say that you're searching for something. Let's say you want to find a number that's a palindrome. So you go through here and you find your 33 and you're happy. But you still have to keep on trudging along to the very end, because that's how the recursion works. There's no, so what you could do in Java is you could throw an exception and say I'm done, and thereby terminate the recursion like that. But what if you actually wanted to look for all the palindromes? You look at one, you want to do something with it, later say, gosh, maybe there are more, and you want to come back. Now, the way you implement that in Java is very different. You use an iterator. You would use a tree iterator, and the tree iterator kind of holds state. Have you ever implemented a tree iterator? Well, it's a standard assignment. I'm sure to always make my data structure students do that so that they remember that I want to do it. Because it's tedious, right? Particularly if the tree does not have an uplink. If the tree has an uplink, it's kind of okay, because then you go up and then you go up until you can't go down again and you can't figure that out. But if you have no uplinks, your iterator has to hold a stack of pending nodes, and it's not a fun assignment. But it can be done, but it's not particularly fun. And every time that the tree has a different structure, you have to rethink how you do the iteration. With continuations, it turns out to be almost a piece of cake. The other thing is, as an interesting use case, what if you want to iterate through 2 trees at the same time? Suppose you have two trees that might have different internal structure, but you want to know, is the sequence of leaves the same? With the recursive approach, that would be really difficult. I guess you could have two threads, each of which does, no. You would have to store the value somewhere and then compare them. But with an iterator you can do it, but with Scheme we're going to use continuations. So, this one heard of it. So we want to define a function that the tree iterator function. Tree iterator is given a list or a tree, and this tree-like list. It's a function. It's a function with no parameters. And each time I call the function, oops, there's a missing break here. Each time I call the function, it gives me a new value. It gives 1, 2, 3, and then eventually it gives empty, and I'm done. Now, here's my implementation strategy. I'm going to use the tree each function that you've seen on the previous slide, the recursive visitor. I'm going to call it with a very specially constructed f. The first time iter is called, I'm just going to make that call. I'm going to capture the continuation around the point of visiting. So over here, I'm going to be doing my visiting, and I'm going to capture the point where I'm going to be visiting. And I store that in resume visit. That's some global variable. When I call iter for the second time, then I simply call resume visit. I have to give it some parameter because they all take one parameter, and I'll just give it a dummy atom. And so the second time, I'll come back in the code where it did this recursive walking through, and it'll keep continuing on its recursion. That's how I'm going to get back in. I haven't yet told you how to get the answers out. So this would be, this is more complicated than previously. And previously, the bank robber just wanted to get the money out of the bank and back into the kitchen table. This time, he wants to return to the bank the next morning. So there's two continuations involved. So this time, on the very first time, the bank robber goes into the bank and is about to hold up the ransom note. At that point, he takes a continuation, puts it in his pocket, does his thing with the ransom note and everything, and by the way, takes the other continuation from his other pocket to go back home. But next morning, he takes the one that gets him back in the bank, thereby obviating any of the complexities of the security guards and all of that. So, so we have two continuations. So let's find out where we get the other one. So we need to deliver the result. So I need to return the result back to the point where iter is invoked. So when iter is invoked, I want to come back to that point with the result, and that's what I'm doing in the same way that I've done before. So I take the continuation and I stash it away and return the result. And like I've told you before, then I'm going to do the resume visit thing, which gets me back into the visitation. So over here, where the value is being produced in the visit, I remember this point, and then I call return result, which gets me back up. Now, there's a little bit of fussiness with what do you do at the very beginning, what do you do at the very end. And that's kind of normal, because you need to prime the pump at one point, and we'll do that. So that kind of gives you more realistic use cases. And I think at this point here, you'll see why I didn't want to spend a lot more time to look at this stuff, because it's not all that instructive. But it is instructive for you when you review this thing at home, as you surely must, because it's going to be a confusing mess right now, to go through it one more time with the information that you now know, because it's going to make it appear somewhat less senseless. So if you think of these continuations as these super go-tos, then I think these simple things are going to become more helpful the second time around. So one's just going to have to do this. So in this lab, we'll have another simple but useless continuation, and then we're going to do the tree iterator. And really, all the tree iterator exercise is to copy and paste the bits and pieces that you've seen on the slides in the right place. But of course, they look confusing, and it's going to take you some amount of time to wrap your head around it.